In this video, we'll continue our discussion of section 2.4 and 5, exact equations, by doing another example of a exact DE. There's a typo here I'm going to mark out. Your notes probably won't have them there, but that shouldn't be there. Okay, so let's rewrite this out. I got 2ty over t squared plus 1 minus 2t. All of that is going to go with dx minus ln t squared plus 1 minus 2, all that's going to go with dy equals 0. I can tell because this is a dy dx. I can tell what I would multiply by dx, and it would capture that other problem. Okay, so I have an m then. Checking now to see if it's exact. M is that whole first expression, 2ty over t squared plus 1 minus 2t. And we want to take that partial with respect to y, the other variable, not dx, but the other variable y. This becomes 2t over t squared plus 1, because t in this case is the constant. So this is like having 3 times y. The derivative of that with respect to y would be a 3, right? Well, we have that here, right? It's just this function times y. So if I take the derivative, I get that function out front, which is considered a constant in this case. Okay, so we have that. We also have, I don't want to write with a highlighter, n of xy is negative ln t squared plus 1 plus 2. Remember, we take the sign with us. So that tells me if I take the partial here with respect to, not m, but n with respect to x, or t, not x. We don't have any x's here. T is our x. Then I have 1 over t squared plus 1. That's the derivative of ln of something. Chain rule gives me a 2t up top. These two things being equal tells me dE is exact. I guess we should have a therefore. Therefore, dE is exact. So since those are the same, then I know that I can find a gamma. My gamma of xy, I know I can snag that either from m or n. My notes, I go with m, so let's do that. If I take, and that's not an x, by the way, back here, this is a t. This is stuff I'm going to do this whole time. I'm so used to x. Anytime they change it, I just, the whole time. If you want to change at the very beginning to be a t and not an x, all you have to do is write let t equal x. And then change all the t's to x's, and you can work it out. I don't care, as long as you just say it up front. All right, so if I want gamma, then I take the integral of mty with respect to t, because I know m, it was a partial with respect to t to get m. So I plug in everything there, all of m, so 2ty over t squared plus 1 minus 2t dt. Okay, this is going to be a u sub. Y is a constant. And then the u sub that's going to happen is if you let u equal t2, t squared plus 1, then you actually just get the numerator. So it's 1 over u, which is going to be an ln of u, but our u is t squared plus 1. Pause and take the time to do it if you need to do it. Then we got minus t squared. Plus some function of y. Not c, because it was a partial that we're undoing. So now I have that gamma function is equal to that. I can go ahead and find the gamma function with y because I know that's going to be equal to n. So I take this now and I do it with respect to y. So I just get ln t squared plus 1 for the first term. The t squared's gone, and then I get plus h prime of y. I now set this equal to n of ty. All right, that's there at the top. I got negative ln t squared plus 1 plus 2. All right, so it looks like something the negative, where did that come from? Oh, in my notes, I went the wrong way. Okay, so this should be, for it to work out, this should actually be a positive. So do me a favor. I apologize this happened. I meant to change it before I taught this video. Make this a positive for me. and also make that a positive. All right, so that changes this. There's no negative there. I messed up anyway when we did our partial. There should be a negative. A lot of you guys may have caught that. So that fixes that problem, and then also that'll fix right here. Okay, great. I apologize for the mistake there. It's going to happen. I'll make them as least often as I can. I have the ln on the left and right, so those can just go away. So I have h prime of y equals 2. That tells me that h of y is equal to 2y plus c1. So now I have y of ty, or sorry, gamma of ty as y times ln of t squared plus 1 minus t squared plus 2y plus c1. Oh, we don't need a bracket there. Right, so that's my gamma, and the theory tells me now that because I found that function, that very beginning in dE can just be written like this. The derivative, because I'll get all the crazy chain rule stuff out of this, will equal 0, for sure. Which means if I integrate now both sides, I get y ln of t squared plus 1 minus t squared plus 2y plus c1 equals c2, because the integral of 0 is a constant. I'm moving that over now. Y times ln t squared plus 1 minus t squared plus 2y plus, or equals, I do that every time, equals c. That is my general. There was an initial condition, so using y of 5 equals 0, we're going to plug everything in here. So 0 times ln of, it doesn't even matter what goes in there, minus 5 squared plus 2 times 0 equals c. So we are going to get a negative 25 for c. So our answer is y times ln of t squared plus 1 minus t squared plus 2y equals negative 25. That is a fantastic answer. The interval of validity, if we go through, the only thing that raises some flags, we have some fractions. So let's go back up to look. We have this, but if you look at the denominator, t squared plus 1, you can't make that 0. Try to find a t to plug in to make it 0. It doesn't work. You could use an imaginary number, but that we don't want to do a calculus on imaginary numbers. That's a different ball game. The ln is the same game. It can't be 0. Well, it can be. It can't be 0. Same game. I can't make that 0. So we actually don't have any problems throughout this whole thing because of that. T squared plus 1 will never be 0. So the answer is all real numbers for our validity answer, or interval of validity. All right, there we go. That's another exact. In the following videos, we're going to talk about what if it's really close to being exact. Is there something we can do or consider to make it exact?